Hello and welcome to lesson 1.3. Today we're going to look at sets of numbers, ordering fractions, inequality symbols, and we're going to review absolute value. As a review, let's review sets of numbers. The first type of numbers we have are natural numbers. These are numbers like 1, 2, 3, 4, 5, 6. Sometimes they're referred to as counting numbers. We also have whole numbers, which are essentially your natural numbers, but it also includes 0. Then we have integers. Integers are like whole numbers, except we also have opposites of the natural numbers. So this would be negative numbers as well as positive numbers and 0. And then we have rational numbers. This is any number that you can write in the form of a over b, or in other words, you can write it as a fraction. Now don't let that fool you though. Sometimes rational numbers can be written as a decimal too. However, what you're going to notice is that the decimal itself will either terminate like it does here, and by terminate we mean that it has an end or it stops, so 6.27 and that's it, or you're going to see that you have a repeating decimal. So in this example you can see that we have 8.2 repeating, okay, and repeating decimals can also be written as a fraction. And ultimately, all integers, if you recall, are considered rational numbers, okay, because we can write them as a number over 1. So if I were to look at the number 2, let's say, 2 is really the same thing as saying 2 over 1 or 2 divided by 1. So because I can write it as a fraction, this is considered a rational number as well. For example 1, it says to name the set or sets of numbers to which each number belongs. So for part A, we have negative 12. Well, negative 12 I know is an integer because it's a negative whole number, okay? And then it's also considered a rational number because all integers are rational numbers. So I'm going to write rational number like this. For part B, 5/12, this is not a fraction that will reduce down into an integer or a whole number. So this right here is just going to be considered a rational number since it's in fractional form. Part C, negative 4.67. Because I have a decimal place and it terminates, I know that this is a rational number. And for part D, 6. 6 is just a whole number, and because it's positive, we can also call this a natural number. So natural whole, because it's both a natural and a whole number, it's also an integer, and all integers are also rational numbers. Now, when we're looking at sets of numbers, sometimes we have to decide whether or not a set of number is really reasonable for our specific situation. And this is more for kind of like your real life applications. So here I have an example, and it says, if you have 110 kids going on a field trip and each bus holds 40 kids, how many buses do you need? So to figure this out, we're going to take our 110 kids that we have going on the trip, and we're going to divide it by the 40 kids that are able to ride on one bus. So if you do the math and you divide this out, you're going to see that we end up with 2.75 buses. Okay, which sounds great. However, in the real world, you can't really use 2.75 buses. What this really means then is we're going to have to bump that up, and we really need to use 3 buses in order to fit all 110 kids. So in this situation, 2.75 is considered a rational number. However, we really need to bump that up to an integer or a natural number because we have to have a whole bus. We can't have partial buses. Example 2 says, which set of numbers is most reasonable for each situation? When I look at part A, it says an outdoor temperature. Well, if you're living in Michigan, we know that we have positive temperatures, okay, in the summer months and most of the year, okay? We do know that there are times where we can hit 0, so that would mean I would have at least whole numbers now, not just natural numbers. And then in some cases, we even hit temperatures below 0 or in the negative region. So I would say that you could probably say that we would need integers to represent temperatures. And if we look at part B, it says the numbers of beans in a bag. Well, typically if we're counting beans, okay, these would be considered natural numbers because we're going to start out with 1 bean, then 2 beans, then 3 beans, and so on. So these would be natural numbers. So by now you're probably asking yourself, well, what about numbers that cannot be written as a rational number or cannot be written as a fraction? These right here are what we call irrational numbers, and that's because they cannot be written in the form of a over b or as a fraction. Okay, some classic examples would be something like pi. Remember, pi is a number that will continue on forever. The square root of 10 is another example. So when we take our rational numbers and our irrational numbers and we put them together, we get a set of what we call real numbers. And visually, this is what it looks like. So you can see the narrowest band that we have are our whole numbers, where we have zeros, we have, like these right here are all going to produce a whole number. So 4 divided by 2 is 2, we have 6, square root of 25 is 5. So these right here are all whole numbers. Then if we want to broaden our horizons just a little bit, we can include their opposites or negative numbers, and these are considered integers. Then if we go a little bit farther, we can now include decimals and like terminating decimals, repeating decimals, or fractions, and these are our rational numbers. So this is one half of our real numbers. The other half of our real numbers comes from our irrational numbers, numbers that are going to not be able to be written as a fraction. Things like this that will continue to repeat. We have pi, okay, and so on. So the two of these together create what we call our real numbers. Now sometimes you're given a situation and you have to determine what type of numbers you need. Okay, so if you're sitting there thinking to yourself, oh, okay, I need to have a rational number, but you're able to find what we call a counterexample, then your number is no longer considered rational. So a counterexample is an example that proves a statement is false. You only need one counterexample to prove that something is false. So one case will prove that it's false, but you may have many supporting cases, but as soon as you have one false case, it is no longer false. Or it is no longer true, I apologize. Okay, so if we look at the example, it says, is this statement, all integers are whole numbers? Is this true? If it's not, let's think of a counterexample. Okay, so as I think this one out, in my head, I know numbers like 1, 2, 3. These are considered whole numbers. I can include 0 as a whole number. That's still an integer. However, once I start looking at my negative numbers, stuff like -1, -2, -3, and so on, these right here, these are integers, but these are not whole numbers. So this right here is my counterexample that I would use to prove that this is not a whole number. So for example 3, it says, is each statement true or false? If it's false, we must list a counterexample. So for part A, it says all whole numbers are rational numbers. So as I sit there and I think, whole numbers start with 1, we have 2, we have 3, and I guess we could even start with 0. And I can turn all of these into a fraction just by putting them over 1. So these right here are definitely considered rational numbers. So here, I would say that this is true. Part B says the square of a number is always greater than the number. And that would be true in the case of something like 2 squared, which is 4, 3 squared, which is 9, and so on. However, if I look at something like 1 squared equals 1. So this one is not greater than this one, so this would be my counterexample, and I would say that this is false. And I would say it's false because it says is always greater. And this here is a counterexample as to why that's false. For my second part A, it says all whole numbers are integers. And remember, we have 0, 1, 2, 3. These are considered integers because they're the positive integers. So this here would be true. And for the second part B, it says no fractions are whole numbers. So I would agree that stuff like 1/2, 3/4, 5/8, and so on, these are definitely not whole numbers. However, if I look at something like 4/2, 10/5, okay, 4/2 will turn into 2, 10/5 will also turn into 2, so this and this is both considered a whole number. So for part B here, this is going to be false. Okay, and just to review comparing numbers, remember that this first inequality symbol, because this is what these are called, these are inequalities. Okay, this inequality here, or the first one, is considered a less than. The next one down is considered the greater than. And then if you recall, once we go and we add that little line underneath it, like as in this case here and this case here, that means it's going to be less than or equal to. So we can write that in. So less than or equals to. Likewise, the next one is greater than or equal to. And finally, we have this symbol here that kind of looks like an equal sign, but it has a slash through it. So this is going to mean not equal to. So not equal to. And we're going to use these to help us compare some numbers. And as a quick refresher too, remember that when we're ordering fractions, sometimes it's better to rewrite the fractions as a decimal and then we can compare them. Okay, you may also choose to plot your fractions on a number line so that you can see which one comes first and then second and then third and so on. So for example 4, it says order from least to greatest. So these are all negative numbers. So because they're all negative, I have to figure out which is the smallest negative, and then the next smallest, and then the greatest negative fraction. So the first thing I'm going to do is I'm going to convert these to a decimal. A negative 3/4 is really a negative 0.75. A negative 7/12 is really a negative 0.583, and this 3 is going to repeat. And then the last one, negative 5/8, is really a negative 0.625. So if you were to plot these on a number line, okay, you could see which one is smallest. Or if you remember, when we're dealing with negative numbers, like all three of these are, the biggest value is really the smallest one when we're dealing with negative numbers. So in that case, I can see that the negative 3/4, this is my smallest, and the 7/12, because it's a negative 0.5, this is actually going to be my largest. So if I were to compare them, I would go a negative 3/4 is less than a negative 5/8, which is less than a negative 7/12. And this right here is now written in order from least to greatest. Please let me know if you have any questions. Otherwise, I hope you guys have a great day.